Oh, I'm still trying to tune this Ten Tec Pegasus radio that's probably circa 1999 or so. And it uses RS-232 um, in ASCII to tune itself. So anyway, this has been a real interesting problem for me. They have these tuning factors to tune this radio for transmit. The receive works okay. I found some software from a guy, and now I think it might not be right for Python, but this was done before Python was popular. So they wrote this thing in the late 90s when C programming was the soup du jour and Python was a glint in someone's eye. So anyway, you have to set transmit tuning factors on this thing, and you give it this T command and then all these um, high and low order bytes to tune this radio. And so I found that I couldn't calculate this stuff accurately with the formulas that they gave us here. So I thought, well, I'm going to start down at nothing. And so at nothing here, you want to simply tune this oscillator. Let's see which one. Yeah, this one. So this thing will go in 2.5 kilocycle steps here. So you want to get the coarse tuning factor for this one and the fine tuning factor. So if you're not within 2.5 kcs, this one can tune 2.5 kcs as a fine tuning, which they say it's on DSP, and this one's all on RF board analog. Anyway, so they give this little table here of when you pipe in these frequencies here into the program, it should put out this stuff here for the local oscillator one, and it should put out this for the fine tune. And this has been a real interesting bugger challenge here. So I finally wrote this little program here in Python that if you give it the frequency in this table, and they have a test chart. So if you put in these frequencies, I want to get out this number here and this one here. So coarse tuning and fine tuning. This has not been easy. So I found because of the precision in Python, I guess I could have used NumPy to do it, but NumPy for huge precision, I didn't want to get involved with importing NumPy into a radio program. So here I have a frequency in megahertz, and I'm trying to match up the table here. And I found that this conversion factor they gave me works generally, but I've had to put in some correction factors. So if my frequency is less than 4.0, I can divide with 2503 kilohertz. Um, if it's less than 20, I want to use that 25004 to get it right. And then if it's greater, I want to use, and then 20 megahertz, I want to up to 30, I want to use this correction factor. So that's because of the precision of Python and how it rounded up and rounded down. It's really, really difficult to get this figured out. Anyway, so I finally did get this working with this formula here. And I call that keeper because I was so desperate to make this work. Anyway, let's see how it goes. So if I put in now from the table, and I was trying this on the Raspberry Pi too. The Raspberry Pi the Python did work on the Pi the same way as this Mac OS computer. So that was a good thing. And I'm trying to find the actual tables again. Here they are. So how can we do this? So there's my table right there. And if I put in, say, this frequency of 0.1 megacycles, I should get this stuff out. And sure enough, there's my 0.1 right there. Let's run the program. And I should get 18039 and a 0 in the table. 18039 there and a 0. So that lines up. And then they have little examples here for testing the fractional part of the fine tuning. So you can put in 0.1 and 0.1. Let's try that. Let's put in that there, and that matches, and hit it. Run the program, and you'll get 18039 100, which should agree in the table. Anyway, so I finally got this all to match up. This has been laborious. And like say for 5 megahertz, we should get this and that. Let's put in 5. Anyway, so now I'll put this into the transmit tuning and see if I can tune the transmitter. I've had no luck in making this transmitter work with their formulas. And this is taking me days to figure out. So yeah, so for 5 megahertz, I get coarse tuning 1999 with a fine tuning of 0. And sure enough, 5 megahertz, there's my 1999, and I got 0. Now you can make this a little different here. You can put in, say we'll put in like 10.0015. Let's try that. 10.0015. Run that program, run it like that with a frequency 21.999, 1500, which looks good. Anyway, this is taking a while. 21.999 and 1500. I just keep losing windows here. There we go. So yeah, there's our 10.0015, 21.999, 1500. So that works out great. We can go 11 here now. I wonder if I can cut and paste this. I doubt it. Can I cut and paste this number? Let's see. I did a cut. Let's try a paste on it. Will that work? It did. Look at that. And now that comes out to be 2239910. And 22399 and 10. So yeah, so this thing is now accurate finally. And I can now put it into the transmit part of my program and see if my transmitter will go. Of course, there's all this stuff about offsets and everything that I haven't figured out yet. This is just basic tuning. So yeah, I found their manual this table is really useful. I still got to figure out what this stuff here means. And I got to figure out all this stuff, but just getting these basic coarse tuning and fine. Gosh, I did it this way. The way I did it. I didn't use this at all. It doesn't seem to work to match the table down here. And this BFO, I'm not even sure where the heck BFO is in this thing. I don't see a setting for it. So I guess I'll make that 0 and then use cubic SDR to see what this transmitter is actually doing. So this has taken me days to figure out. All right, well, that's what's going on with my little Pegasus and my amateur radio programming stuff here. It's tedious, and should I be doing this? I don't know. I did this stuff back in my 20s. Early 20s, I wrote device drivers, and there isn't much work for device drivers, but that's how it is. Okay, well, thanks for watching. Have a great day.